I'm very happy to present you our work on obfuscating wide area network traffic at line rate. This is a joint project together with Roland from armasuisse and Laurent Vanbever from ETH. In the past, it has been shown over and over again that even though traffic is encrypted, it still leaks a lot of information. For example, just by looking at packet size and timing information, people identify which video somebody is watching, what operating system, browser, and application somebody is using, and many more things. And all of these attacks, they leverage the fact that encryption only slightly changes packet size and timing information. And while most of these attacks are focusing on internet traffic, we argue that wide area networks are at risk too. Because these networks, they connect multiple sites of an organization, such as different data centers or campuses. They spread over large geographical distances, and they are therefore fairly easy to eavesdrop. In fact, major operators of such wide area networks, such as Microsoft and Amazon, they acknowledge that their traffic is at risk, and they say that they do not only encrypt their traffic on the application layer, but also at the network layer using an encryption scheme called MACsec. When we look at preventing traffic analysis attacks in a wide area network, we are faced with three challenges. The first one, of course, is that we want to have high security. The second one is that we need to have high performance because these networks, they often run at hundreds of gigabits per second. And the third one is we need to have a system that is deployable without changing the hardware or the clients and servers. Ditto addresses these challenges as follows. First, it makes the observed traffic independent from the actual traffic. Second, it uses an efficient pattern to reduce the overhead and therefore achieves high performance. And third, it runs entirely in the network data plane, therefore it does not require any changes to the servers running in the data centers. Of course, we are not the first ones to look at preventing traffic analysis attacks. But most of the existing work, they also look at preventing these attacks in the internet, which forces them to accept some trade-off between efficiency and security. And therefore, they do not have the same security properties as what we will be presenting. Second, they only provide fairly low throughput, often megabits to a few gigabits per second, something that is enough to work in the internet, but not enough to work in a wide area network. And third, they would be difficult to deploy because they require changes on the end host or servers. So looking again at the networks that we want to protect, this is, again, a visualization of a wide area network that connects multiple sites of an organization. We assume that we have a programmable switch on the edge of each of these local networks. Now, these are actually not very special devices. These are devices that everybody can buy. And in such a network, we can then protect all the links within the wide area networks. These are all the blue colored links in this picture. And we protect them against an eavesdropper that can eavesdrop on one or more links in this network. And this eavesdropper can receive all the traffic that is crossing these networks, including the metadata such as timestamps. But since the packets are all encrypted, we assume the attacker does not have access to the contents of the packets. And in such a network, we provide three security properties. The first one is what we call volume anonymity. This means that the attacker cannot determine the size of packets and flows. Second, this is what we call timing anonymity, which means that the attacker cannot determine the time between two packets or the length of a flow. And third is what we call path anonymity. This means that the attacker cannot track packets across multiple protected links in the wide area network. Taking a step back now and looking at how these traffic analysis attacks works. We have here an example of traffic that is sent over one link. Each of these green rectangles represents one packet that is sent at a certain time with a certain size. And now a traffic analysis attack basically looks at the packet sizes, the timing between two packets, and by comparing this to our previous knowledge, the attacker can say, if I see this shape, for example, this is a Skype call. What we want to do, on the other hand, is we want to have a network where this shape that the attacker sees is always the same, no matter what is going on in the network. For example, it could be like shown here, that we send the same size packets at regular intervals all the time. In this case, the traffic analysis attack is no longer possible. But the challenge now is to reshape the traffic from how it looks on the left to how it looks on the right. And this is usually done not only by us, but also by related work, by adding padding to packets, and by introducing dummy packets to fill gaps where there is nothing to send. However, if we would do it like this, and we just make all the packets the same size, this would be very inefficient, because as you see, there is a lot of yellow in this picture, and yellow is essentially padding or overhead. So whenever we need to add padding, we use up bandwidth on the link, and we want to minimize this in order to be efficient. So what we do with ditto instead is we compute an efficient pattern beforehand, given the distribution of traffic that we expect in the network, and then we do not make all packets the same size, but we send packets of different sizes given the distribution that we expect. This still provides the same security properties, but it makes the system more efficient. So, and this is basically what ditto is doing in the network. In the remaining of the talk, I will provide you more details about how we compute these traffic patterns, about how the traffic shaping in the data plane works, and I mentioned some of the evaluation results that we got from running ditto on real hardware. So first, about computing efficient traffic patterns. Here, we basically want to compute a traffic pattern that is minimizing two types of overhead. The first one is what we call padding. These are bytes by which we make the packets larger. And the second one is what we call chaff packets. These are packets that we introduce when there is no real traffic to send. And because of hardware constraints, we want to have some repeating pattern of a certain length, maybe 3, 4, 5, 6 in this order, in order that this pattern can later be implemented in hardware. We find that a pattern is efficient on average if it matches the distribution of the traffic that is expected in the network. I will explain you this with a very simplistic example. In this simple example, we assume we have a network where 25% of all the packets have size 500 bytes, 25% have size 1000 bytes, and 50% have size 1500 bytes. And we assume that we want to compute a pattern of length 4, so a pattern that uses potentially 4 different sizes of packets. The way we compute it then is just by taking the distribution that is shown here on the left, and we compute the equal interval percentiles, the 4 equal interval percentiles in that case. That is the 25th percentile, which is the first pattern state. This is 500 bytes in our distribution. The 50th percentile is 1000 bytes, and this is the second pattern state. And the third pattern state is the 75th percentile, which is 1500. And the fourth pattern state is the 100th percentile, or the maximum packet size in the network, which is also 1500 here. So this is already how we compute the traffic pattern. Now that we have the traffic pattern computed, we need to enforce it in the data plane. And for this, we leverage recent advances in network programmability, which allow to run custom algorithms in programmable switches. These switches, they are commercially available. Everybody can buy them. They follow a certain architecture called programmable switch architecture, and they impose a lot of constraints on the actual algorithms that one can run and on the operations and the resources that are available. So actually, the main challenge behind this project was to implement this seemingly simple idea in a way that works at line rate on these programmable switches. Giving you a bit more details about this. We now look at the same illustration as before, input on top, and we want to reshape it into the shape from the bottom. The switch then uses 3 operations to do this. First, buffering. This means to hold one or multiple packets back until they fit into the pattern. The second one is padding, by which we make packets larger. It's important to note here that we always make packets larger, never smaller, because splitting packets or fragmentation is something that is not possible on these devices. And the third operation is insertion of chaff packets, which means we fill gaps when there is no real traffic to send. Now, the way these devices work is that they process packets in a pipeline, and this is more or less how the pipeline for ditto works. At the end, when everything else is done, we encrypt the packet. So this is just using what is available on switches. For example, MagSafe is available in hardware, can run at line rate. And we have seen before, it's also already used by major operators. Before we encrypt the packet, we make sure that it has the right size. And to do so, we add padding until the packet reaches the destination size. Now, adding padding is not something that is available on the switches by default, but something that is available is adding custom headers. So we just predefine a set of custom headers, and depending on how much padding we need to add, we add another combination of these headers to reach any possible packet size. Before that, we ensure that the packets leaving the switch are following the right pattern. And for this, we use round-robin scheduling. I guess most of you know how it works. It's The scheduler iterates over a set of queues. Here we have 4 queues, each of them assigned to one of the pattern state that we computed before. And then the scheduler will automatically send one packet from each queue and then start with the first queue again. This is nice for us because it already implements this repeating pattern that we want. But there is one case when it does not work, and this is when a queue is empty. Because when a queue is empty, then the switch will simply skip it. This makes perfect sense in a normal switch, but it's a problem for us because it would violate the pattern. So to make sure that this does not happen, we ensure that these queues are never empty. And we do this by prepending another level of queues. These are pairs of priority queues, one pair for each round-robin queue. And in these pairs of priority queues, we have a high priority queue that is filled with the real traffic, if there is real traffic, and a lower priority queue that is always filled with chaff packets. So that the combination of these two priority queues always has a packet to send, and therefore we never have empty queues in the round-robin scheduling. So that's basically how the switch works. There is one more thing that we need to ensure, and this is again that these chaff packet queues, they are never empty. And as a constant source for them, we just recirculate chaff packets through the switch. This means basically sending the packets from the switch to itself, and we use this kind of as a traffic generator. And we always clone them into these queues. So that's basically what the ditto switch is doing. In practice, it's a bit more complicated what we do here because this hierarchical queuing with 2 levels, this is not something that is possible directly in these switches, but we have developed a workaround that makes it work. So coming back now to the security properties that I mentioned in the beginning. We now have volume anonymity because the traffic always follows the pattern and it's independent from what is actually going on, because any gaps that when there is no traffic to send would just be filled with chaff packets. We have timing anonymity because the traffic is sent at a fixed rate. In our case, it's just the maximum rate that the link supports. And we have path anonymity because on each link, the pattern is always enforced and all the packets are encrypted, so it's not possible to track packets based on their contents. So this is how ditto works. And next, I will show you some results from our evaluation. We performed 2 types of experiments. One type of experiment is running on the real hardware switches. The other one is in simulation. And we use simulation to see what would change if we could slightly modify the way the hardware works. And the one thing that we would like to modify is that when the round-robin scheduler hits an empty queue, it would inject a dummy packet instead of skipping the queue. But for time reasons, I will only cover some of the experiments that we run on hardware. The first one is where we measure the throughput that ditto can achieve. For this, we send packet traffic to ditto with a rate between 10 and 100 gigabits per second, and we measure how much traffic is coming out. Ideally, of course, we would like to have the output rate being equal to the input rate. And what we see in the results is that this holds up to a point of about 60 gigabits per second for this traffic trace that we are using here. And then the overhead that even ditto adds starts to take an effect, and the performance plateaus slightly below 80 gigabits per second. In this experiment, we also add simulations of some of the related work. Now, it's important to know here that we simulate these works in a very generous way, and that is, we only take into account the overhead that they produce. All of these systems, they run on hardware that would not run at the speeds that at 100 gigabit speed, or at least we don't have this hardware available. So we basically assume one can run these systems at an infinitely fast machine. And then even if one could do this, we see that ditto still outperforms them. Now, the next experiment is one where we measure different application level characteristics. For example, the load time of a website. We see again that up to about 60 gigabits per second, we have no effect, and then the load time starts to increase. Here, this is for a pattern of length 6. What is also interesting is if we take shorter patterns, that means patterns that are less well fitted to the actual traffic distribution, the performance starts to degrade. And especially if we take a pattern of length 1, this means making all the packets the same size, something that a lot of related work is doing, we see the performance drop already at 40 gigabits per second. So that shows that having these longer traffic patterns actually improves the performance clearly. With this, I'm at the end of my presentation. I hope I could show you that ditto provides a secure, high-performance way to obfuscate wide area network traffic, and it can be deployed without changing clients or servers in the network. Thank you for your attention.